Welcome to this explainer. If you've ever driven past a massive oil and gas plant, with those towering metal columns and that endless crazy maze of piping, you've probably wondered how on earth engineers keep those gigantic, highly flammable structures safe from disaster. Well, today we're diving headfirst into the high-stakes world of industrial plant design to uncover the reality behind one of their most absolutely crucial defense mechanisms, fireproofing. It sounds straightforward, right? But the engineering that actually makes it work is incredibly clever.
All right, let's clear something up right off the bat. When you hear the word fireproofing, you probably picture some kind of magical, impenetrable shield. Like you might think it means the structure literally cannot burn, no matter what. But the reality out there in the field is way different, and honestly, a lot more pragmatic. True fireproofing in these extreme environments isn't about building an invincible fortress. It's actually much more of a strategic sacrifice. It's a highly calculated engineering decision that is all about just surviving long enough.
Because in highly volatile environments, where a single spark could ignite a massive hydrocarbon fire, the entire goal of fireproofing boils down to one very specific number: 2. The whole objective is just to buy exactly 2 hours of precious time. Here's why. Unprotected structural steel loses about half of its load-bearing strength when it hits around 600 degrees Celsius. And a raging hydrocarbon fire? It can reach that temperature in mere minutes. So fireproofing is meticulously designed to delay that critical, structure-failing heat for exactly 120 minutes.
So what's so special about 2 hours? Well, that specific window is basically the ultimate lifeline for everyone on site. It stops the main equipment, those huge vertical vessels and massive pipe supports, from buckling and collapsing. Because think about it, if a massive tower comes down, it's going to rupture other pipes and tanks, and you get this terrifying, unstoppable domino effect. Securing those 2 hours gives operators the time they need to safely evacuate and shut down critical valves. And critically, it gives firefighting teams the exact window they need to get in, set up, and start containing the blaze.
Okay, so how do we actually pull this off? In the industry, we call this passive fire protection, or PFP for short. You can think of PFP as a dedicated stunt double for the main structural steel. See, active fire protection, like sprinklers or alarms, needs a trigger or an action to work. But passive fire protection, it's just always there, built right into the structure, silently waiting. When the flames hit, the PFP takes the absolute brunt of the heat, absorbing and deflecting that energy so the main steel underneath doesn't just warp and fail on the spot.
To build this time-buying armor, engineers traditionally go heavy. I mean really heavy. Workers will literally spray a super thick, incredibly dense concrete-like substance, usually something called Fendolite, directly onto the equipment supports. We're talking the base skirts of vertical vessels or the legs holding up massive tanks. By slathering this stuff on, they create a heavy-duty thermal barrier. The fire has to literally bake its way through this thick layer of artificial rock before it can even begin to threaten the steel hiding underneath.
But hang on, this brings us to a really fascinating engineering puzzle. Picture a perfectly smooth vertical metal support skirt. Now imagine trying to spray heavy, wet, concrete-like mud onto that completely smooth vertical surface. Yeah, gravity is definitely not your friend there. So how do you stop this heavy armor from just sliding straight off before it even cures? If that fireproofing falls off during application, or even flakes off years later from plant vibrations, that steel is left completely naked and unprotected during an emergency.
The solution mechanical engineers came up with is honestly wonderfully simple, but it works like a charm. They just weld M10 hex nuts straight onto the support structure. They space these nuts out evenly, usually about 300 millimeters apart, and they basically act as tiny iron-clad anchors. So when that wet fireproofing is sprayed on, it wraps around and grips onto those little nuts, locking the heavy concrete securely against the vertical steel. It creates this permanent mechanical bond that completely defies gravity and handles decades of wear and tear.
Now you might be wondering, who actually decides which pieces of equipment get this intense heavy armor? Well, it is definitely not a guessing game. It takes a highly coordinated 3-step workflow. First, the process and electrical teams get together to assess the raw material risks in a specific area. Once they have that data, the firefighting and safety teams step in to officially map out the hazards and draw the legal fireproofing zone. And only after all of that does the mechanical engineer step up to apply the specific design, calculate the extra weight, and add in those required gripping nuts. The big takeaway here is that a mechanical engineer designing these massive structures they literally can't work in a vacuum. They have to wait for the official fireproofing zone drawings from the safety teams before finalizing anything.
If a piece of equipment happens to fall inside that zone, the engineer has to go back, update their blueprints for the nut welding, and completely recalculate the support strength just to handle the crazy added weight of the concrete. It really is a perfect symphony of cross-team collaboration.
But here is where things get really cool. The whole industry is actually going through a massive evolution right now. We're seeing a huge shift away from those bulky, labor-intensive concrete sprays like Fendolite and moving toward highly advanced Intumescent fireproofing paints. To the naked eye, it literally just looks like a thick coat of standard industrial paint. But the chemical properties inside this stuff, they completely change the game for how modern plants are designed, built, and maintained.
Because it goes on like standard paint, the benefits are huge. First off, it adds way less weight to the structure. And remember our gravity puzzle? Because this paint has incredibly high adhesion, it completely eliminates the need to weld thousands of those little M10 gripping nuts. When this high-tech paint gets exposed to extreme heat, it undergoes a rapid chemical reaction, puffing up into a thick, charred foam that instantly insulates the steel. It gives you that exact same critical 2-hour thermal barrier, but without all the heavy lifting.
So that leaves us with a pretty fascinating question to wrap up this explainer. We've seen exactly why that 2-hour window is an absolute necessity for saving lives, and the crazy lengths engineers have gone to secure it, from welding thousands of tiny anchors to spraying literal tons of artificial rock. But as materials science keeps accelerating and these intumescent paints get cheaper and more reliable, how soon until heavy concrete armor completely disappears from industrial design? Will the plants of tomorrow rely 100% on paint that magically transforms into a heat shield? It is a brilliant reminder of how innovation keeps our most dangerous industries safer every single day. Thanks for hanging out with me for this explainer, and keep questioning how the world around you is built.